Okay, 3. Okay, we're live.
Okay. Sometime we could try doing this on Zoom and see how the audio quality or whatever is.
Yeah, I'm open to that.
Okay, I think we're all here. This is kind of just a discussion, me seeing if I'm in sync with everyone on the case for sparse activation. And I really just wanted to point out, there is one nuance I want to point out in the biological argument that I just think it's a fun thing to discuss, the different directions it could go. So my main thing here is just sanity testing that I understand this, and is also just acting as kind of a useful review and touching base. And one interesting point on the biological argument, and maybe like half a point at the end about like when it comes to like temporal memory and stuff.
So random thoughts.
Yeah, sure.
It's good. No, I think it's good. I don't want to
Yeah. Well,
You just did.
Okay. So I've divided the board into two kind of not equal halves: biological case, computational cases for sparse activation, for having a small subset of the neurons active at any point in time, and biological or artificial neural networks. So the basic biological case, of course, is activation in cortex is sparse, and therefore we have a proof of concept that that a system like this can work with sparse representations. And not only that, not only can it work, that's the way cortex does it. It's the proof of concept we might want to mimic it. So the nuance I wanted to bring up here is I've drawn an axis here of the axis of to what degree do you believe that deep networks capture some truth about the cortex?
Deep network being artificial.
Yeah, artificial deep networks. And I would say, like, and I worded this a little bit carefully just to say that you can believe this. You can believe that deep artificial networks capture some truth about the cortex, and they leave out a ton of truth as well. You might think that that maybe they're similar at doing how they do flash inference, but they're not similar in the way that they handle time. You might just think that there's some core truth there, but it also misses a lot. But there still might be some core truth there that's interesting about it. So I've quantified like this axis of to what extent you believe this, or to, how extremely you believe it. At the bottom is deep networks don't capture any truth about the cortex. And then I'll go from the top down just because it reads a little better after that point. Are the units, the individual neurons of deep networks analogous to neurons in the brain? Or are the individual units in a deep neural network analogous to groups of neurons of the brain? Maybe multiple neurons actually act as, like, maybe each perceptron unit is actually implemented by a population of cortical units, cortical neurons. And there's an easy way, like just using some of our neural mechanisms I could show. For example, here's just a one-layer network. These individual units of this network could be implemented either by a ring of pyramidal cells. You could have like a ring, so a bump of activity is representing a scalar, or very similarly, we have something called the scalar encoder that we've used before that uses a population code to represent a scalar by moving a bump of activity along it. It's fundamentally the same, it's just not periodic. So just to give you a mental image of one of these versions of how a group of neurons could implement a perceptron unit. Or you could step back even further and be even more hand wavy and say that like there's not really an analog of the deep unit in cortex. You can't point to any one thing or any group of units and say this is that. But there is still some way that the computation is just similar enough that they have similar results. The computation of a deep network and the computation of cortex they have similarities, even though there's no direct analog between units.
So can I, when I saw this chart and you just explained it, I thought it was upside down. And in the sense that if I were to think about the levels of analogy between deep learning networks and the cortex, I would say, okay, there's no analogy, that's your bottom group right there. Then the next thing I would say is, okay, well, there's an analogy between the neurons, but that's it.
Okay.
And then you can go next and say, oh no, the groups of neurons are doing something similar. And then at the top would be the overall computation is similar. Like, so to me, to say the overall computation is analogous to say, oh, yes, if the cortex is doing, reference frames and 3D modeling, then, then these artificial neural networks are doing the same too. So I just found I'm trying to understand how I would have taken those three items and flipped them around and as you came up this way.
Interesting. This is, I see where you're coming
If
from.
you were saying, if this axis was deep networks capture some of the truth about pyramidal neurons, maybe I would have accepted this, but you said deep networks would capture some of the truth about the cortex. So I think of the cortex as this really sophisticated computations, and deep neural networks don't. Therefore, the overall computation being analogous would be at the top of the thing. And I'm just pointing out that I'm not sure why you felt it was the other way.
Well, I mean, I feel like a lot of people, I don't think I'm alone on this, that well, just like, I mean, this vaguely resembles Mars 3 levels of like, is the overall computation the same? Figure out, okay, these two systems might do the same computation in fundamentally different ways. Now figure out like the representation of whatever his terminology is. I think mine sort of mirrors that, the idea of figuring out what is the algorithm of the brain. You can implement it using using probabilistic programming. You can implement it using all these things, and I'm kind of going up in that level.
Yeah, but you see where I'm coming from? I can say like, oh, I could say that I have real neurons, but I'm doing something completely different with them. So that would mean that having sort of modeling real neurons would be one step up from nothing. It's like, yeah, I got the same thing, the neurons are the same, but everything else, the circuits are different and the computations are different. So it's like if I'm adding more and more detail, I would start with neurons, then circuits of neurons, and then overall computation. So I just want to point out that you could look at it completely differently, and I would have done it differently, but it doesn't matter as long as I understand what you're trying to get at.
I just learned something from what you said. So,
And the way I've been seeing it, kind of the deep networks, particularly like these convolutional networks, they model maybe 1% of the synapse in the neocortex. And there's tons of circuitry that's not modeled at all. And so it's not so much about, is it analogous or not analogous? It might be analogous to 1% of what's going on. But there's all of this other stuff that's not at all captured. And of course, the learning algorithm also is quite different, typically in deep networks than the neocortex.
So I guess you provided a line here, we could all interpret that axis different ways. So I don't think, hopefully that's not the critical element of your talk here. I'm not sure.
I mean, just the point I was ready to make now is that if you argue that, if you say neuron activity in cortex is sparse, therefore activity in deep networks should be sparse. I feel like that applies if you...
That's the first one, probably.
Yeah.
The closest.
Yes. If you believe this. So the way I've drawn this, these are more and more intense levels of belief. You can, so I'm not framing it the way you framed it. That's also another way. But saying like, okay, they're similar in some hand wavy way, or in some just general way. They're similar, like they're quite similar. The units actually fit in. You can actually make these mappings, or the units are literally units. And I would say that like this case is 100% convincing if you believe this. It's moderately convincing if you believe this.
With the case being?
That because activity in here.
Well, we know that neural activity in the cortex is sparse.
Yes.
That's a fact.
Yes.
Right,
But suppose the correct mapping from deep artificial networks to cortex is this. Activity in this network would be sparse in the sense that like a very small portion of this ring might be active, or a very small portion
So
of
you're
this.
saying each artificial neuron really could be represented by a set of neurons?
Yeah, like
and
suppose
then you get
each,
sparsity.
let's just go with one crazy idea. Suppose each mini column is a ring, and every mini column has a bump of activity.
Yeah.
At that point, yes, the overall population is sparse, but these things would not be sparse.
Yeah.
And
A similar argument was made, it has been made multiple times about the many active dendrites, where people say, well, I could just, I can model a neuron with, 50 point neurons, because each point neuron would represent a segment of the dendritic tree. And so a neuron, a biological neuron is actually a network of, I can model with a network of, so it's a similar type of argument there. Where I can say, oh yeah, the neuron is really actually a bunch of other, or the parental neuron is a bunch of these other point neurons.
Yeah.
Marcus?
Yeah.
Related to what Jeff said, I was thinking, is there another line there where you could say a unit is related to, groups of units are related to a neuron? Like I've seen people describing each unit as like an integrated segment.
Yeah,
fair.
Seeing a lot of
that's even higher up than, yeah.
Is that what I just said?
It's
Yeah,
a little
yeah,
bit, it's a
yeah.
little bit what you
That's
just
it,
said, that you could, maybe you're right, that here I've been assuming a unit is more complicated than a neuron, because it can do arbitrary scalars. But yes, if you now get into the fact of multiple dendrites, you're totally right. I didn't think that into this argument. I don't know where that fits from.
Yeah, that would be higher up in the chart. Like,
But it would be higher up in.
One neuron is a group of units.
Yeah.
It's so interesting that I still have trouble flipping around my thinking to fit your chart. And there's nothing wrong with your chart. It's just like my way of thinking about it is different. And it's like interesting that we can come up with different ways of thinking about the same thing. But anyway, I'm going with it.
Okay.
So,
And I would say, I don't think there's any big consensus in the community about this either. I think I've seen deep learning, people who've thought about the biology talk about it, making multiple, some people talk about it, as you said, it, some people up there, some people in the.
well, most people in the machine learning community don't know any of these issues about neurons.
But yeah, that's why I qualified it as some people who
Like
thought about
if you
it.
pick out like the top experts, most of them have a little bit. They've interacted with the neuroscience.
A little bit,
department.
but I've also seen them say things which I think are really just crazy, and because I have a little bit of knowledge, and a little knowledge is dangerous. They reach incorrect conclusions about biology. But anyway, I think your point is there's different levels at which we can look for analogies between deep learning networks and biological networks. Right?
Yeah, and
you're somehow going to bring in sparsity into that.
And I think particularly with sparsity, this is a very relevant question. Are we really literally doing a population sparse coding in deep learning, or can we just model it by assuming every unit is already represents a population? And in that case, maybe you don't need sparsity.
Yeah, like we're using biology to give us a set of clues about where the treasure is in deep network space, like how we can find better deep network solutions using biology as a clue. And knowing where you are on this axis or a similar axis really changes what you might pursue. You might try to make the neurons binary if you think this, but you might do something totally different if you think something down here. And it just feels like a useful thing to keep in mind as you combine it, as you take these punchlines, like neuron activity is sparse, and what conclusion you draw from that depends on where you are on this axis.
I'd say maybe my view, and maybe our view, I don't know, but is that it's units, they're not neurons today, but they should become closer to real primal neurons.
Okay.
That's my view.
Yeah.
So I would, say I'd like to be here, but units becoming really biological neurons.
Okay.
Consider that.
Okay. Yeah, that's pretty much my whole biological shtick. I felt this was a useful thing for me, and I wanted to put it out there and see what you said to get in sync with you more. On the computational cases side, so this is, I can go through 1 through 5 pretty quickly here. And I just tried to break this into multiple pieces. So I started with something pretty conservative and just said, like, everything might still work with sparse activation.
Everything meaning every artificial neural network.
Everything. Yes. Sorry. Yeah.
The brain's
Deep,
work with sparse activation.
yes. Deep networks should still work with sparse activation, and if they do, there's a lot to be gained from that in terms of
That's,
efficiency.
by the way, that's not obvious to me. I mean,
No, it's not obvious to me.
Okay, so,
I changed at first. It said should. I changed it to might.
because they were not designed with that thought in mind.
Yeah.
And, we talked about the width of them, there's so many issues, but, we're betting that they can work and be more efficient.
Yeah.
And our understanding at the moment is they can.
Well, can't you say like dropout and autoencoders basically kind of make that case?
No, not really. So dropout does sparsity kind of randomly, and they kill off some percentage of it, and that's only during training. So it's not really sparse activation.
So when it's finished,
They basically kill cells
Right.
randomly.
to
During
make it
training.
more robust.
To make it more robust, but it's not really sparse activation. At inference time, there's no
Okay, but
dropout.
autoencoders kind of do.
No, autoencoders, there's no sparsity.
It's just a small number of units.
Well, you're basically forcing it to code down, so.
Yeah, but there's no
that's-
sparsity. It's a smaller representation, but still
There's a
dense.
difference.
Yeah,
From a large dense to small dense.
Yeah. There's a big difference between dense and sparse. It's different from small and big.
But you start off with something large, you
You make it smaller,
make it smaller,
but not sparse, dense.
but it's dense, but smaller. I mean,
Yeah.
you could have had zeros all across there, and that would look like a sparse layer.
Yeah, but I don't think sparsity implies dimensionality reduction, right?
Yeah.
Like
No.
just as sparse.
No, it's almost the opposite. You want high dimensionality and sparsity, ideally.
Right.
Okay.
It's like, imagine you did the top 5 principal components of a data set,
Right.
right? That doesn't make it a sparse representation. It's just a denser, it's a still dense, but a smaller number of dimensions.
Okay, so
It's like a
basically,
projection to smaller dimensions.
so in that sense, it says, I'm trying to find the top K, the most important features, but I'm neglecting everything else, so I'm compressing the space down.
Correct.
Right, but you're saying that that doesn't count as sparsity because it's explored, it started off with a large space and then subsetted it, right?
It's projecting down to a smaller number of dimensions.
Right.
Yeah.
Okay, so you're drawing a distinction between projection and what we're.
Well, sparsity to me is, you have mostly zeros. And you could trivially do it. You could take something that's 3-dimensional, add 1,000 zeros, and just keep it always zeros. So yes, it's sparse, but it's not really capturing the spirit of sparsity, right? It's just still basically 3-dimensional and dense.
Okay, I'll talk about it offline because I still have an issue.
I don't think people think about autoencoders as being sparse unless you explicitly make them sparse.
Okay.
This is also an idea. I'm thinking about that.
But that's what Bruno did. For example.
Which brings us to, okay, another case to be made. This one is the one I probably understand the least about, is how it works, like intuiting why. But enforcing sparsity through something like K-winners changes the tuning of units in a way that's maybe beneficial. So if you make it where like a neuron that's not, if a neuron doesn't activate because K-winner suppresses it, it wants to go learn something else, and it causes your tuning curves. It causes the receptive fields of individual units to move apart in a way that might cover the input space better. And I listed here, like it's very much like the spatial pooler or House of Dense paper, and it kind of goes back to like Bruno's stuff with sparse codes, and he has a similar thing going on there. And so,
Yes, I think this is a key thing for
Yeah.
our research. This is really a key question.
Yeah.
I would kind of change the wording a little bit. It's not necessarily changing the tuning of units, but changes the representation of a layer in a way
Okay.
that's beneficial. It's a broader statement in
Yeah,
some
yeah,
sense. And I would say in the machine learning community, this is not clear at all.
Yeah.
It's not clear at all why sparsity would help other than efficiency.
Mhm.
We think it does, but
Yeah.
I would say in the machine learning community, there is no clear answer.
and now to throw in a couple of things that are obvious to some of us, sparsity it makes pooling easier, probably. It makes here I've drawn a picture of what I mean by pooling. I'm using the way we usually describe it. It's vaguely related to the way the machine learning community describes it. Here at time step 1, maybe these input units are active, and we want this output unit to connect to them. A different time step or there's no time here, a different epoch, different whatever, like a year later. Ignore me. So the point is,
It could be the next time. So.
Yeah.
I mean, if my finger's moving over the coffee cup, it'll be the next time.
Yeah. So at some later point, these inputs are active, but you know through some supervisory signal that this unit should be active. It connects to those. And all of there's no disruption, no confusion between the weights. That's one just core building block that you might encourage more of that kind of thing in deep networks by making the representation sparse. And then also on a related note, unions. So the idea that you could have an input be ambiguous and so you activate multiple representations and continue activating multiple representations up through the network. It's not super clear to me whether that'll work if these are dense and you're just adding them up. I really don't know if that'll work. We know this will.
I don't think you can do a union with dense representations, can you?
But I don't know what's going to happen if you add up. If you think of each of these, like you represent a cat with like a dense vector of these, all these, like this might be like 55, 10, 3, like they're just numbers. You represent a dog with a different vector and you add those vectors up. What will happen? I don't know.
It seems fairly intuitively strong to me that it's not going to work.
It seems intuitively strong to me that this will work. Our way
Our
works.
way will work,
yes. But I don't have intuition about
We know
that.
the sparsity work. You can intuit, you can deeply understand unions. Because when you have sparsity and you do a union, you're really not throwing away the representations. They're both there still and they don't interact. And
To hold the Berkeley crowd though, Spencer and others, and Canerva, don't they say that you can do superposition of stuff with dense representations? They have that whole set of operations on how you can do it and recover it and stuff like that.
They definitely
It's much harder to think about.
Yeah.
But mathematically it might still work. I don't know.
The way they do it, they can even do it with dense binary codes. But it gets worse and worse the more you union, of course, the more you superimpose. But their vital piece that they have is they, on top of it all, they have an auto-associative memory that's able to take a portion of a code and activate the entire code.
Okay.
And that's a key part of theirs. That's a computational necessity for theirs.
They need a transformation. And they had that key, and they need that key to transform the matrix.
Right.
So it's not
But those could all be dense.
they can all be done.
I think that the reversal operation will subtract the other one.
Right.
Now, one thing I wanted to point out here, I think people have probably thought about this, but it's we're not going to get this for free. We'll have to do just a little bit of work. K winners. If we're always enforcing exactly K winners, we might not get
that
this.
very well.
Right. So like it might be we want to do K winners during learning, but then like during inference, maybe we let the K winners be a little less dramatic.
That's the K inference factor.
Okay, there you go. So then
It's kind of a hack.
Cool. So
Is that something that floats around? Or is it that K inference factor? Or is it?
It just loosens the restriction on the K winner, so it's not K, it allows it to be a little bigger than K.
But it's fixed, or is it allowed
It's
to
fixed.
float?
It's fixed. But it should be allowed to float ideally. If we do it like in the temporal memory and stuff, or we should want it.
Because I think it would be something that would respond to boosting and stuff like that, right?
Yeah. I don't think winner take all, it's sort of at odds with unions.
okay, and now the final part is where I now bring in our other algorithms into it, like temporal memory and everything else. So fifth reason, we have a bag of tricks based on forming associations between sparse representations. We're really good at like learning these kinds of things, and they sometimes bi-directional. So we have that, like here I've depicted temporal memory. You have a sparse code associated with another sparse code, associated with another sparse code. And of course, you know what the temporal memory does. Here I've sort of depicted, this is physical space that could be thought of as grid cell space, and associating.
Those are sensory motor modeling.
Yeah, this is sensory motor modeling, associating these with these codes, and then these sparse codes eventually mean B at that location, A at that location. And here I've done just a quick picture of voting, of having a bunch of sparse codes that represent objects, the object identity, and having them vote for each other. So we have, once we have sparsity, we have kind of it kind of opens the door to introducing these things. For me, like, this is my least well-formed sentence or question for this whole presentation. I don't know how to do this yet. I don't know how to combine this with deep networks. There's not
That's
like
the caveat.
Obvious, straightforward way, or at least I don't know it yet. Of like, if you my mental model or a mental model of what deep networks are doing is they're taking this high dimensional input space and finding the shape of the boundaries of the classes. And like, this is the class of coffee cups. And like, if a point is somewhere in this space, this high dimensional space, it's a coffee cup. And these are markers. It's kind of inherently doing generalization. It's kind of inherently saying this big region is coffee cups. And these mechanisms, to me, feel a lot like building graphs, or building graphs and connecting them to each other through associations, but taking nodes, taking these representations, these codes, and connecting them to each other, and kind of building a big graph of locations to features, location to feature, or A to B to C to D. And my last point I'm saying is just, I don't know what to do here quite yet. I'm still learning, but it's, I don't know how to make the connection between these yet.
Deep learning networks and bag of tricks.
Yeah. And that's a great point to end with, is I don't know, but like that to me, that's still it might work. I just don't see it. I don't see the path quite yet. I'm still thinking about it.
Yeah, and I would say I don't see it either, but that's kind of our research agenda.
Yeah. Okay. I have a different way of thinking about it. Maybe it's with Shem.
Yeah, go for it.
I don't want. I need some space to write.
Cool. Yeah, I'll take a picture of the board, and then it's all yours.
Point to me where you want me to write.
At this point, anything
How
can be
about I
erased.
erase the left hand?
Yeah, you can even reverse it if you want.
Yeah, no, I'm just erasing it. Anyways, I didn't think this way anyway, so it's.
Thanks, that was good.
Yeah. So I don't know if this is the way you guys think about this or not. This is what I think about it, right? So you got these deep learning networks. If there's any artificial neural network for the last, going back to perceptrons, you know, you got these networks, multi-layer networks that are connected. And this is what these basically are doing what you said here. They're basically taking a series of inputs and that are labeled, and by using their labels and a backpropagation learning algorithm, you end up with a representation up here that is more separable, and then put a classifier on it. Right? But that's all it's doing. There's nothing else. It's just taking a bunch of labeled things and sort of rearranging the representation so that you can classify it. There's no other deeper knowledge about anything. So if you recognize it as a cat, doesn't know what a cat is, doesn't know what cats look like, can't tell you what cats sound like or anything like that. On the other hand, so this is great for classifying labeled data. And then over here we have the brain, and now we know that in the brain you've got, in the neocortex, we now understand that a single cortical column, of which there's about 150,000 in your brain. A single cortical column is a very complex structure that learns basically, if you want to call it, 3D models of objects in the world, including how they behave. And this is all based on a particular small sensory patch, not a big thing. So this relies, like, I'm going to put a whole image in here, but over here, I'm going to just put like a small sensory patch, just one little piece of the retina, a sensory patch. And I also have a motor signal. So given a small sensory patch with the tip of the finger, the retina, and a movement, I'm able to build this, learn a complete 3D model of that object or my body and other things. It's basically all cortical comes in, and this is a very sophisticated function here. And so we have like one thing here, which learns it built through movement, is able to learn complex structure and behaviors. And then we have 150,000 of them. And this is something completely different, right? This is just a classifier. And so the challenge we have is, even if we understand this 100%, what's going on here, this is so different than what's going on over here. It's kind of hard to take what we've learned here, the bag of tricks, if you want to call it that way, and apply it over here. I didn't know that any of it would be possible. So Subotai proposed a year ago. He said, look, originally I thought we would have to go start implementing this. And he said, no, look, I think we can take some of the things we've learned from here and apply them to here. And so he said, I said, yeah, what's that? And he goes, oh, I think we can take the basic idea of sparsity, which we know this is sort of a substrate of this thing. It's not like, all the mechanisms here depend on sparsity. He said, we can take that substrate and maybe we can make these things work better. And I know that's interesting. And so the idea there was, we don't have to work in a whole separate world and convince people we have to build brain-like structures. We can just start with this thing and prove that one component, that one little thing really improved this. And then it wasn't clear if anything else from here would move over. It's not clear to me at all that you could bring in these other ideas and bring them over to here. Maybe you can. I don't know. I don't know if that's true. But my thinking was, and Subotai, if you've got more thoughts about this, speak up. My thinking is like, hey, if we can make the case that sparsity really makes a huge difference over here, then people might pay a little bit more attention to people who say the biology makes it important. They might start saying, hey, what else can happen over here? What else do I need to know about that we don't know about? So I don't think all these principles can be brought over into this world. I think one can be brought over, hoping that's the case, maybe a couple more. But I don't think the goal here is to end up building these deep learning networks that have all these features. I don't think we can do that. The ultimate goal is to go start building cortical columns that do a gazillion more things than any of this stuff ever did. And so it's an interesting question as to how many of these principles can be brought over here. And I started off by not knowing if any could be. Subotai proposed sparsity. Great, maybe that's going to be super good. Maybe we could bring over some more. I don't know. I think that's not the end goal. This is all to get people to start paying attention to this stuff. Where they might say, those brain people aren't so stupid. They're thinking about this stuff, and they've been really able to improve our stuff by thinking about the brain.
It's funny, I would have drawn the arrows exactly the opposite.
How's that? Explain that.
It's like a pen to
It's like, so I would say what I'm trying to do is,
Yeah, I misrepresented you, I guess.
no, that's okay. This stuff we know works really well on many practical examples. And my thinking is we bring it closer to here by adding sparsity. All right, and so, and then we want to add in, active dendrites.
Yeah.
And location-based representations.
But
And so each time we're transforming this.
But
into
once
the end goal is here.
Once you end up adding locations, it doesn't look like this anymore.
No, and I'm saying that my goal is to end up here.
Oh, yeah, okay.
So I wouldn't say
No,
I'm taking this and moving it here. I would say I'm starting here and moving it this way.
Well, but
That makes
isn't it true that for sparsity, we are trying to basically, since we're focusing on existing problems, existing networks, and showing that they work better, at least for sparsity, we're going this way. We are saying you can take an existing deep learning network that does an existing problem, and you can make it better by adding sparsity. To me, that feels like you're adding sparsity to this. Like, we're not trying to create a whole new domain of AI. We're just saying, I think the ultimate goal, I hear maybe we can do this.
I think we're agreed on the ultimate goal is to be here.
Here's what you want to go this way. I'm going to argue you're going to go this way with sparsity. But the success of that will get people to go this way with active dendrites, locations, orientation, motor, all that stuff. It's sort of like, to me, this is like the first, would be a good analogy. I don't know,
Yeah, I just, so, you know, I don't think we're doing this, I think we're doing this.
But aren't we trying to go out and show that these existing networks work better with sparsity? Existing problems?
Yeah, so we're adding sparsity
So,
to the activations,
yeah,
and we're adding sparsity to the weights,
Yeah.
which means constraint, and then we're adding, continuous.
but we're solving the
structural
exact, but
plasticity.
we're solving the exact same
No,
problem.
may not be,
Well, initially we are.
initially we are,
Yeah.
because that's just because we're closer, you know, we're
Well,
closer here. But,
I
and soon, like when we get to continuous learning and things like that, we may not be doing the same.
so I
thing.
may, yes, okay, so maybe that's my distinction. My distinction is the initial things we're trying to do here, we're trying to take it, you guys are all working on existing problems that have existing benchmarks and trying to show that we beat these things in various ways. So to me, that means like, when I say here, you're working on the exact same problems that AI researchers already know about and the exact same data sets. As soon as you start adding this stuff, you're gonna be working on different data sets. Different
Yeah, but
benchmarks.
even in the first case, even though we're working on the same benchmarks, our goal is not to beat the benchmarks. Our
Well,
goal is to show new properties.
Yeah, but
of
it's new
benchmarks.
properties but it's important that we meet the benchmarks in terms of accuracy, but we want to show these new properties like.
That's right, yeah.
Yeah, but it's
So
still
shouldn't do
It's still the
significantly
same
worse.
problem. I mean, it's essentially the same data sets, it's the same
For now,
back propagation. Yeah, I understand.
Yeah.
So, but to
and that's
me,
because to me, I'm like just a little bit here now,
okay.
but to me, this is the end goal.
Yeah, I agree, but I think it's gonna be a hard break. I think this at some point, there's either we're working on the same problems that everyone else is working on, and then there's gonna be some sort of break. We're saying, you know what, we're not doing those problems anymore. Now we're doing something else.
Yeah,
And
we need to move towards newer problems.
yeah, but to me, I thought the brilliance of what we're doing right now is just to say, let's just prove that we can improve upon what existing out there. And then, but I still feel it's gonna be hard. I just don't feel like Marcos, it sounded like you were suggesting, how do we add more and more things into this? I'm thinking, I don't think it's gonna work. I don't know, but I do think we have to go over here. And to me, that feels like a jump. It's like, this doesn't feel like a continuum. We're adding sparsity here, and then we have to have a discontinuous break at some point and say, we're gonna do some new problems that other people haven't done before. Anyway, I think we all
I
agree.
agree.
We need new problems for sure.
Yeah.
Right now, we're trying to focus on new properties.
Yes, the properties. I mean, part of the point of the book I'm writing is to make the case that I want AI researchers to realize what's going on over here and to, sit there when they're, oh my God, how, we can't do that with this. We need to build these models of the world, and they have to have all the sophistication, and this is just not going to get you there. Anyway, I think we all agree that this is where we want to go, right? In the future, we want to have these equivalents of cortical columns. Anyway,
We have to.
yeah, we have to. I mean, it's inevitable. But not everyone believes that. Most people don't think that at all. They don't even know about it. So, but it's obvious now to us.
One of the seductive things about CNNs was that it was shown early on that you can emulate any function with a linear sum of inputs. In other words, you can by adding it stepwise, piecewise, you can get any exponential Gaussian, any number of things in there with those units. I'm just saying that was one seductive part of it, is saying, oh, well, if it's Turing equivalent to any function.
It's not Turing equivalent. So it can do any static function.
Static functions,
So,
exactly.
yeah,
Right,
so, but it's not
right,
convolutional.
right.
So it's not limited to convolutional, even non-convolutional networks, but nonlinear. You have to have nonlinearities.
Right.
Then even with the one hidden layer, you can map any static function.
Right, okay, I misstated, but that was the seductive part of the fact that it says in some space, it looks like a complete representation of
Right,
space. What I see what's happening here is they're saying, well, that's fine, but there's a lot of power in the topology of the network and the dynamic topology.
It's not just power. It's just focus on the static issue for once, right? This system is a completely dynamic system. It has to learn through movement. And there's no other way of doing it. And you have to learn the structure of the world and through movement. And it's a dynamic, time-based system, and this isn't. And it's like, yeah, you can map a static function out of this, but you can't possibly map the world into a static function.
Well, what I was trying to say is that that's what you're adding, is you're adding dynamic networks to this.
But it's just calling it dynamic. It's really, it's just shortchanging it, because then someone might come along and say, oh yeah, well, we can add dynamic, properties to this, we'll do.
I don't think so. I mean, I'm trying to use it in the most general sense, in the sense that if you look at what you're doing with the sparse activations, for instance, is basically you're dynamically changing the topology of the network. Connections are activating, deactivating, going dormant, coming back. That's a dynamic network. Now, the point of it is that you have with a CNN, you have, I can do a function and I can have an activation and I can get an output. But if I want to have to even come close to the cortical column, this dynamicism has to be, there's got to be a principled way of adding it, a principled way of having this network mold itself to what's going on around it.
Yeah, but it still becomes very shy of what's the power of what's going on over here.
Well, you have a representation from the neurophysiology that works. Okay, it's based in data. It's based in what we know about neurophysiology. I'm just saying, as a bridge, you have to be able, if you're going to make a claim that these networks can't do what we're doing, you're going to say, what does this thing have? Not what it apparently can do, but what does it have?
All right, so the answer to that question isn't sparsity. The answer to that question, sparsity is this low-level substrate that's really not the argument. The argument is learning n-dimensional models of the world, including the behaviors of objects, and learning the n-dimensional models of my body, and so on. And so to represent a model of structure in the world, you need to have reference frames. You need to have the concept of a location in reference frames. You need the concept of an orientation relative to those reference frames. You have to have the concept of the state of the reference frame to represent the state of the object, that has different forms and shapes and so on. It all is built upon movement. These are the things that are what a cortical column does. I wouldn't start off. It's funny, I wrote the whole book so far about talking about what cortical columns do, and I didn't mention sparsity once. I didn't need to mention sparsity. That's not the key thing. The key thing is the reference frames, the locations, the orientations, the movements, just you learning this model of the world. And there's nothing like that here. There's no n-dimensional model of the world with movements and how to get someplace and to manipulate things. And, it has to incorporate all of robotics and everything. So to me, the sparsity thing is a very weak argument. It's just, all we're just saying is, hey, you know what, we can just, this is something you learn from the brain. Look how much it makes these things better. But that's not why we have to go to the bottom. We have to go this way because of all this other stuff that these things don't even begin to do. They're not even thinking about this stuff.
Dynamicism encompasses more than just sparsity. I mean,
it's not even just dynamic. I want to talk. It's got to have reference frames. It's got to have, locations and orientations.
Those are inputs, right?
No, this is the representations here. This thing represents a column. Has each column has layers of cells that represent thousands of reference frames, and they have the orientation and they have where you are. This is all the knowledge of the world that a finger knows is in this column. And you can model complete objects. These reference frames are in here. The orientation is in here. We spent a lot of time talking about where these cells are in the different layers and how we're representing these things. These are not inputs here. The only input you might have to this are a motor and a sensory input. And all the modeling is occurring in here. So this very sophisticated modeling function that has all these things, you can't get away from that. They have to be there. It's not someplace else. It's there. And it's actually 150,000 copies of these things in your brain. So this is the thing we have to convince people of. I don't know what else to say about it.
No, I think you made your point.
Yeah. So how we bridge between these two things is an interesting question. But I think at least we're all aligned, super aligned, that we need to end up over here. This is not just a dynamic CNN. That's not what it is. This is a system that has reference frames and orientations and different types of states in it and so on. It's a very complex function. that happens to be built out of neurons, but the neurons, the reference frame neurons, the grid cells, if you will, cortical grid cells behave on one set of principles, and then the orientation grid cells, have different set, and the equivalent place cells, different set of principles. They're all neurons, but the neurons make them function in different ways. So here you have this very uniform structure that just basically has one idea, and here you have to have like a half a dozen or a dozen of things that are each sophisticated, but at least we know what those are, and we know a lot about how they work.
Like I said, maybe it's not a bridge, it's a jump.
I think it is going to have to require a jump at some time. I think what the sparsity work we're doing is, it's almost like let's do a physical bridge metaphor. So let's say there's a bridge that goes between these two. Here's the bridge over, and people are walking over the bridge, and let's say, what we're doing is what we're doing right now is we're walking this way, and we say, look, I brought you something from this world over here. We're bringing you a thing called sparsity, and look how great it is. Look how it makes your network so much better. Why don't you follow me back over here, and I'll show you the rest of it. Because I don't think we can bring all this over to this space. It's just not going to work. And of course, we'll have to figure this how it goes. But but at least we all agree we have to end up over here.
I think if we get the current stuff of having sparse activations, sparse connections, and learning those sparse connections dynamically, I think that will be a really strong set of neuroscience-based things for convincing people.
I think we need to have both. We need to have see, this stuff actually does help. And oh, by the way, look at the rest of this, and maybe you'll have the epiphany that this is what you need, and you need to move over here. Because that's it. That's the answer. There's no question in my mind that the world's going to end up over here. So our job is how do we convince people that now? It's not an if. It's going to happen. So anyway, so it's going to be both. We're going to show you that it helps here, and we're going to somehow get you to start thinking about these things, and then you'll realize that the AI world will realize that they have to do this. That's just the way it is. I mean, that's what our framework paper basically says. This is a framework for intelligence, and you need this. This is the framework. You got to have it. There's no other way of doing it. And that's the case for the book. That was a long conversation on it. It's a good start, Marcus, for getting us talking about them. Any other people want to make counter arguments and additional arguments? Speak up. What would be interesting perhaps is to see if there's other things we can bring over beyond sparsity and still work in the domain of artificial neural networks. You mentioned the active dendrites. Is it possible to add active dendrites to these guys and show additional properties, but still solving the same problems they're solving today? But they're not solving the sensory motor problems today, at least not in any way. So eventually we will have to move from these problems to a different set of problems.
So what class of problems did you have some thoughts as to what class of problems we would need to move to?
Well, general intelligence is like, modeling the world. Think about it this way. There's no real separation between AI and robotics in my mind. That intelligence is a sensory motor modeling system. And so you have to have systems that have behaviors and move. The sensors have to move somehow in the world. And the classic neural networks, that's not true at all. There's just an input and that's it. And
wouldn't you say that continuous learning is a new problem that we're trying to embark upon in terms of representation?
I don't think it's a new problem. It's just a better way of learning of the same problem.
Right, but isn't that one of the things you're kind of bringing across?
I would say that's an example of a key property we want to show, that these systems can learn in a continuous manner.
Right.
I think it's best shown actually with new problems. It's really hard to show it with MNIST or something.
Right.
You need new data, a new framework or not framework, but a new paradigm, if you will, of thinking about how continuous learning
I'm
works.
just wondering if there's an exit problem out of there that we would know that continuous learning.
Well, Vincenzo can talk about a couple.
Yeah, I don't think continuous learning is a new problem. It's just a new property. It's just an improved property. Well, you could imagine, unless you're doing a voice word spoken recognition system, right? You recognize spoken words. And right, you have a training set. You train the system, and all right, now it recognizes spoken words. Well, maybe people's dialect changes over time, and maybe the number of people using it change over time. So you can have a continuous learning system that basically you don't have to retrain the system at any point in time. It's just retraining as people use it. And that would be the same problem, slightly better performance and continuous learning, but it's not really doing anything new. I'm not sure how beneficial that is.
Well, I mean, one of the problems that's kind of out there is the problem of one-shot learning. So I'm just wondering if that's a step toward.
One-shot learning could really comes from sparsity and the dendritic, sparsity and active dendrites is the ability, it gives you the ability to do sort of one-shot learning. I don't know if it gives you the ability over here, but it does give you the ability over the course.
Yeah, it depends what people mean by one-shot learning, because it might require the full kind of reference frames and.
Yeah, I know. So I know that we understand how one-shot learning occurs over here very rapidly. This doesn't do a gradient descent, back propagation over here. You just form the synapses once and you're done. That's it. Instantly, you can learn new things. And we understand how neurons do that here. It's not clear that you can actually add them here. I don't know if you could. You might be able to, if these are sparse and you had active dendrites on all this, you might be able to learn something new here really quickly.
Yeah, I don't see why you wouldn't be able to.
So that could be that could be another thing we bring over the bridge.
Right. Yeah. I think of it as this way.
Okay.
Whatever.
But to me, is the AI researchers are all over here, and they don't really want to look at this.
Yeah.
They just don't really want to think about it. So that's why I feel like we're coming over this way and walking into their world and saying, you don't really care about neuroscience, but let me help you out doing something you're already doing here. That's why I think it's this way. And then we're trying to get them to follow us back.
I think in order to really convince the AI world, you have to show it working really well on practical problems.
Well, that's why we're coming over to their world.
I think it's okay if it's not existing benchmarks. It could be some new, data area or a new problem domain. I think that's fine.
I don't know. Maybe I'm a little more hopeful and maybe naive. I would drive my beliefs is understanding once you understand what this is, then it becomes clear that this is where you have to be. It's not a matter of, to me, it's not a matter of prove me that this does something I can't do here. It's more like, oh, of course, now I understand this must be this way. But maybe other people don't do that, and maybe we need to show them working moment by moment. I'm hoping to convince a large number of people that they, without proving it to them, just once they understand this, they'll go, oh, I get it. But maybe that won't work. Maybe we have to show, problem after problem that it works best. I don't know.
It might be both.
That would be depressing to me if we could never get anyone to realize that this is the right thing. That'd be pretty bad.
Yeah, I think most people, they still are driven by the idea of having always practical problem they can solve. So if you start from algorithms that can work today on real world problems, computer vision application, whatever, then of course the steps should be incremental.
Yeah.
So more in line maybe with these ideas that starting from something that actually works today, you can have more and more properties, maybe principles of intelligence that you can outline in a more free and theory that you're free to think essentially without this very strong constraint on having a system that can work today.
If you look at the history of AI, it didn't start this way. It started with people trying to do sort of big concepts about knowledge representation. You have Black's world, you have schemas, and people were trying to come up with the Turing machine equivalent for AI, and only because they kept failing at it. Now we've backed ourselves in this corner that everyone's afraid to think about anything that doesn't work. It's crazy. And now we've just accepted. My point is that the AI world used to be trying to understand this stuff, and they just have stopped. And now it's become accepted dogma that all you can do is improve the existing practical application. But it didn't start there.
Well, one of the things I mean, what you're doing with sparsity is that you're basically showing, here's how you can add robustness where you didn't have it before, here computational efficiency where you didn't have it before. I mentioned the one shot because I kind of track that literature a little bit, and people are down to, well, I'll have a smaller set, 1/10 the size of the set, and I can train, they're working hard on that problem. If you have a representation that, as you say, ideally works instantly, to take the generality of the schemas and basically say, okay, this is another of this, but it's different in this particular way, and instantly recognize it for what it is. That's a powerful thing. That means that's attacking the other problem. How much data did I need?
Yeah, but that doesn't fundamentally move in this direction. That's basically, you could argue you're solving this problem better.
Well, or you're representing it better. I mean,
Well,
if you have a
whatever.
better representation, which is, I think, what you're claiming, then people would jump.
No, I'm saying that there's two possibilities here. That we can sort of incrementally move people in this direction by showing continuous systems that work better and better and better and better and better. Or there's a point at which we get more and more people to sort of realize that this is the place to be, and they start focusing. It's like, can we get people to think about AI?
I'm with Jeff on this one, by the way.
About knowledge representation, about what it means to be intelligent.
We have to convince people to come towards us.
Doesn't work. I guess that's, we just don't know yet. We just don't know, can we incrementally have working systems all the way along here? Do we have to start get people to start some subset of the AI world?
Blake
to say,
Richards
what,
agrees with us, the
tired of these
neuroscientist, the
We're gonna
machine
start
learning
doing the
expert.
real thing again and working on API.
I think there's gonna be a number of big jumps to get to there that we have to do.
Yeah, I don't know what it'll take to get the research community to go to this level of thinking, but the engineering community, if you give them, a better screwdriver, they'll.
Yeah, I
They'll
understand,
use it, yeah.
but my point is we do have to get the research community to get there. And my point is they were there in the past. They were interested in stuff in the past. And there are, there's a lot of people who are interested in the AGI or general purpose, or, there are intellectuals who really want to understand this stuff. And yeah, the engineering practical world, they may not be paying attention to it. So again, maybe that's another way of looking at it. We need to get bring along the engineering world at the moment, working, and then we also need to excite some sort of, like Jeff Hinton, he's out there talking about capsules and like he's trying to jump. He's trying to jump from here to here, even though he doesn't know exactly what this is. But he's trying to do that jump. He's out there. He doesn't, capsules aren't sort of just incremental improvement on these things. So there are people, and there used to be a lot of them, who wanted to do that big thinking about AI.
It's really sad, it's much smaller now. Almost everyone, even people saying they're doing really basic research, they're really doing engineering, incrementally.
Yeah, so, but look, I think, I mentioned the previous history of AI because it's proof that people will and can do that. It's just, we shouldn't take that's a fact that everyone needs to be working on incremental improvements. If we can educate people and show them and get them to understand the whole brain stuff going on here, they'll do it. They'll move back over there. There'll be a subset of people who just in the research community want to focus on this. It has to be. It's going to happen. So we can't just don't accept that it's going to be like the way it is today forever. Well, there you go. A lifetime of effort in one diagram.
We build bridges.
Well, that's we're building bridges. That's our
That's engineering task.
What's that?
That's engineering task.
Yeah. Oh, okay. So those we're actually just placing these little stones here, right? We're just trying to build this. Few stones.
Okay, should we stop streaming?
Yeah. Yeah, well.
Okay, you guys. Thanks for joining me and the team. Don't forget to like the video and subscribe to our channel. And we'll see you again later. I have more live streams coming this week. So have a great day.